Swayam Prabha. Digital India. Educated India.
Welcome friends to this last lecture of module 3 that is of chemistry of soil organic matter, and in this lecture we are going to talk about in details about the humic substance and metal interactions, and what are the conditions for forming the chelates, and some basic concepts, and then how the pesticide and organic matter interaction and soil organic matter soil and soil clay as well as organic matter interaction occurs, and what are their implications. So, in the last lecture we have already discussed that when two or more organic functional groups coordinate the metal ions to form a ring like structure, a form of complexation occurs that is called the chelation process, and the product is known as the chelate. And here you can see different organic molecules are producing the chelates using the coordinating different metal ions. So, another important term while we are talking about the chelates is the ligand. So, ligand is basically an atom or functional groups of molecules attached to the central atom of an coordination compound, and the type of complexation between the metal ion and the complexant like inorganic and organic ligands like carboxyl and phenolic groups of soil organic matter can be predicted based on two types of factors. One is hydrolysis properties of the elements, and the second is concept of hardness and softness of the metals. Now, again, chelate is a coordinated compound where two or more functional groups of organic molecules basically coordinate a metal ion, and this process is known as the chelation, and ligand is basically the atom or functional groups or molecules which are attached to the central atom of the chelate. So, basically in case of organic compound, these ligands are carboxyl groups and phenolic groups of soil organic matter. Now, these ligands could be inorganic also. Now, what type of ligand is there in case of soil organic matter, particular type of chelate, that can be determined by hydrolysis properties of the elements as well as the concept of hardness and softness of the metals, which we are going to discuss. Now, let us see the hydrolysis properties of the metal. Now, hydrolysis is basically, as you know, is the chemical process in which a molecule of water is added to a substance. Now, inorganic elements can be divided into three groups based on their reaction with hydroxyl and oxygen ion. So, you can see there are three groups. One is called group 1 element, another is group 2 elements, and third one is group 3 elements. So, group 1 elements are basically the elements which basically form the non-dissociated complexes like sulphate, phosphate and oxy acids. As you can see, these are sulphate, phosphates and oxy acids. These are basically group 1 elements, they form the non-dissociated complex like this. Group 2 elements are highly hydrolyzed and can also occur as hydrated cations like ferric. You know, ferric is a hydrated cation, it is oxidized and hydrated cations. Group 3 elements do not have very stable hydrocomplexes even at high pH like calcium and zinc ions, and the major ligand in water is hydroxyl groups. So, ligands other than water will only combine with group 3 elements and to some extent with group 2, but not at all with group 1 elements. So, this is one of the major criteria. Ligands, except from the water, they will basically form the ligands using the group 3 elements. Sometimes they form the chelates using the group 2 elements, however, they do not form the chelate using the group 1 elements. So, this is the difference between the three groups as far as the chelation is concerned. So, if you see here, white square basically denote the group 1, and these dark shaded squares are basically, these are dark shaded squares, these are basically the group 2, and the light shaded squares which we are seeing here are basically belong to group 3. So, based on the hydrolysis properties, this is how we can differentiate different elements into group 1, group 2 and group 3. Remember again, group 3 produces the chelates, most of the ligands except from the water form the ligands with the group 3 elements, sometime with the group 2 elements and not at all with group 1 elements. Okay. So, let us move ahead and see the hardness and soft characteristics for determining the chelating, for the determination of chelation process. Now, before we discuss about the hardness and softness characteristics of the metals, we have to brush up our knowledge of Lewis acid and base. So, as you can see here, this is A basically a Lewis acid and B basically is the Lewis base, and ultimately AB is a basically acid base complex. So, Lewis acid, as you know, an atom molecular ion which at least one atom in which at least one atom has a vacant orbital in which a pair of electrons can be accommodated, and they are an electron pair acceptor. Obviously, this is another feature of Lewis acid. All metal ions are basically Lewis acid. So, we can consider all metal ions as Lewis acid because they can accept an electron pair, where A is the metal ion in this reaction, B is known as the ligand. So, here B is the ligand which can donate a pair of electrons. So, Lewis acid are coordinated to Lewis bases or ligands. Okay. So, this is the definition and features of Lewis acids and ligands. Now, what are the Lewis bases? Lewis base is an atom molecular ion which has at least one pair of valence electron not being shared in a covalent bond. So, it is an electron pair donor. As just opposite to the Lewis acid, Lewis base is basically electron pair donor because they have an extra pair of valence electrons not being shared in a covalent bond, and most anions are Lewis base. As you can see here, this is basically a Lewis base which is donating an extra pair of extra pair of electrons to the Lewis acid. So, based on this, we have there is a classification between hard acid and soft acid. So, what is the hard acid and soft acid? Based on the Lewis acid base complex, hard acid is the acceptor atom of high positive charge, whereas soft acid is the acceptor atom is of low positive charge. In case of hard acid, they will have small size. In case of soft acid, they have large size. In case of hard acid, they does not have any easily excited outer electrons. However, in case of soft acid, they have several easily excited outer electrons. In case of hard acid, they are not polarizable. However, in case of soft acid, they are polarizable. Hard acid prefers hard bases through ionic bonds, and soft acid prefers soft bases through covalent bonds. So, this is how we differentiate hard acids, Lewis acid as well as soft Lewis acid. Similarly, there is some characteristics of hard bases as well as the soft bases, like the donor atom is low polarizability in case of hard base. In case of soft base, the donor atom has the high polarizability. Then in case of hard base, this has the hard to reduce. In case of soft base, this is easily oxidized. So, these are some differentiating characteristics between the hard base and soft base. So, based on this, we can differentiate the Lewis acid and base into 3 categories each. In case of Lewis acid, as you can see, we can differentiate into Lewis acids are basically differentiated into hard acid, transition acids and soft acid. As you can see here, in case of hard acid, we term them group 1 metals, transition acids are known as group 2 metals, and in case of soft acid, they are known as group 3 metals. So, what are the group 1 metals? You can see H plus, lithium, sodium, potassium, beryllium, magnesium, calcium, then strontium, then ferrous, Al3 plus, all these are hard acids. In case of Transition acid in case of group 2 metals basically chromium, manganese, Fe2 plus, cobalt, nickel, copper, and in case of group 3 materials you can see silver, then gold, all these are coming under the group 3 metals. Similarly, in case of Lewis bases we can differentiate in their hard base, transition base and soft base. In the hard base you can see water, then hydroxyl, then fluoride, all these ions, phosphate, sulphate, chloride, carbonate. Most of the anions which are present in the salts are basically in the Lewis bases, and transition bases like bromide, then nitrite, nitrogen, and then soft bases iodide, cyanide, these are different categories. So, you can see classification of Lewis acids and Lewis bases. Now, some thumb rules are there based on this hardness and the different degrees of hardness and of the Lewis acids and Lewis base. There are certain rules. For example, hard cations react to form ionic bonds, that is hard cations react to form ionic bonds. In case of group 1 we know that these are the hard acid like sodium, potassium, manganese, sodium, potassium, magnesium and calcium, and soft cations react to form covalent bonds in group 3. So, basically copper, zinc, cadmium, and transition metals form complexes of intermediate state, that is group 2. Okay. So, these are some rules of based on these are some rules of complexation or based on the hardness characteristics of Lewis acids. Okay. So, also the degree of hardness is given by a formula which is basically this Z square by R, where Z is the charge of the cation and R is the radius of the cation, and the preference of hard metals for ligand atoms decreases in the order of this the following order. So, hard donor atoms and then the soft donor atoms. Okay. Then fluorine followed by oxygen, then nitrogen, chlorine followed by bromine, iodine and sulfur. So, these are the hard donor atoms and these are the soft donor atoms. So, the hard donor atoms such as fluorine and oxygen prefers hard metal ions, and the soft donor ions atoms like iodine and sulfur prefers soft metal ions. So far we are talking about different types of Lewis acids and Lewis base and their hardness classification and their complexation. Now, since we have discussed all these differentiation between the Lewis acids and Lewis base, now it is time to apply those rules into the actual soil organic matter and metal chelates, metal chelation process. So, we can see that the ligands, the complexants or ligands can be classified into three big categories. One is the simple inorganic ligands which are denoted by capital X. They are the major anions which prefer hard metals obviously, and hard sides of natural organic matter we call them NOM denotes by LH. These are the hard sides and mainly carboxyl, and these are basically carboxyl and phenolic acid, because they are the major they are the major complexant or ligand present in the soil organic matter. So, they are known as the hard site, and also there are also some soft sites of soil organic matter denoted as LS, and they are basically nitrogen and sulfur containing sites. So, this is how the three different types of ligands are basically present in nature. Now, let us see how these different types of ligands basically interacts with different metals. So, this picture shows, or this chart basically shows these are the basically the simple ligands. As you can see, these are the simple ligands, as we know, sulfates, carbonates, chlorides, then fluoride, phosphate, all these. So, group 1 metals like alkali and alkaline earth prefer hard ligands, but form weak complexation with them. So, this is thumb rule, one of the thumb rule. So, hence complexation occurs when metal ligand concentration is high and predominantly complexant is inorganic ligand. So basically, in case of alkali and alkaline material, the ligand is formed when the predominant complex scent is inorganic, which is denoted by this capital X. Now, group 3 metals have greater affinity for soft sites than hard sites for simple ligands. Okay, so group 3 metals have high affinity for soft sites than for the hard sites. We know that. Now, group 2 metals like divalent cations have affinity for both hard sites and soft sites. So, these are the basically hard sites and these are the soft sites. In the hard sites, like you can see the carboxylic group, phenolic group, and then this is nitrogen and sulfur groups, and they react with all 3 types of ligand. So, the group 2 metals like divalent cations have affinity for both soft and hard sites and they react with all 3 different types of ligands, and they compete for the hard sites with metals from group 1 and also compete for soft side with group 3 metals. So, this is how they can interact and form the ligands by competing with each other. So, now we have seen the ligands, we have seen the basic concept of chelates. Now, it is time to discuss the stability constant of metal humus complexes. This is very important, discussing the stability constant. Now, the stability constant tells the affinity of a metal for organic ligand. So, it determines the fate of the heavy metal in the environment. If the stability is quite high, it will persist. If the stability is less, then it will not persist in the environment. So, the complexation of the reaction between a metal and either deprotonated ligand or binding site is generally given by this reaction, where this M denotes the metal, Li denotes the deprotonated ligand, and this MLI basically the chelate compound. So, the stability constant for this reaction can be given by this formula, where this Ki, it is basically the stability constant, which is a ratio between this chelate concentration as well as the concentration of the metal as well as the ligand. So, since it is difficult, now it is very difficult to calculate the concentration of these Li, that means ligand. So, basically a more realistic approach would be to calculate based on the concentration of all forms of ligand not bound to M. It is always better to calculate the all forms of ligand not bound to M than to calculate the ligand, specific ligand, by different empirical process obviously. Now, so the another approach where we are considering all forms of ligand not bound to M is basically, in this case we are calculating another stability constant, where MLI, as you know, the concentration of the ligand, M is the concentration of the material, where HXI Li, this term is basically the concentration of all forms of ligands not bound to M. So, we are seeing there are 2 types of stability constant. Okay. So, 2 types of stability constant. Now, these two types of stability constant are basically referred as conditional stability constants. So, they are valid only for the condition like pH, neutral salt concentration. Remember that as the pH and salt concentration changes, they are also variable. So, and this is basically stated for a particular system. So, Ki this is the modified or the second conditional stability constant, and the first conditional stability constant basically related. So, this is basically the second conditional conditional stability constant, which is MLI by M concentration and Li concentration, okay, and multiplied by Li and by HXI Li. So, we can see that this is basically, we can simplify is that by Ki this first stability constant followed by multiplication of the concentration of the ligand by the concentration of the ligand not bound to a particular metal M. So, this fraction is basically is a constant at constant pH and neutral salt concentration. Again, there are two conditional stability constant. The first stability constant which we have calculated is this. The second conditional stability constant which we calculated is this. Remember, for calculating the second conditional stability constant, we considered the concentration of the ligand, which are all the ligand which are not bound to M, and then we can basically simplify this their relationship by using this formula. So, basically the conditional stability constant or the second conditional stability constant, basically the multiplication of the first conditional probability constant multiplied by this fraction which is constant at pH and which is constant at a constant pH and neutral salt concentration. Now, since it is difficult to determine individual, although we have simplified this, but still it is very difficult to determine this individual conditional stability constant. So, basically for that we calculate the average by different empirical relationship, by empirical tests. So, let us see how we do that. So, for that we calculate the average conditional stability constant. So, this is the first average conditional stability constant, where this is the condition, we have already know this, the formula. So, this is the average conditional stability constant. Okay. Now, if we simplify that, it will take this form. So, basically we know that K conditional is, if you see the key condition, we know that it is basically the MLI by concentration of M and concentration of Li. Okay. So, if we multiply it with basically Li in both denominator and numerator, so basically it will give us K I condition and other. Okay. So, basically we can simplify this as K I condition and then we can get these two terms. So, basically you can see it has been simplified, but when we are taking the average by getting this summation. So, basically then how this K I condition came into this equation. Okay. So, similarly in case of K I dash condition also we can simplify it by this condition. Now, we can further simplify it by Cm minus concentration of M, where divided by concentration of M, and then Cl minus Cm and plus M. So, basically here Cm and Cl are the stoichiometric concentration of metal and total ligand respectively. Now, what is stoichiometric concentration? Stoichiometric concentration is basically the ratio of two reactants which are reacting together to form a compound. So, this is the stoichiometric concentration. So, ultimately just like we have seen previously, in case of this average stability constant also we get this type of relationship. So, two average stability constant also we can relate them each other by using this formula. Okay. So, the stability constants of metal HS complex or humus complex are basically affected by seven factors. First of all, source of humus and extraction or isolation procedure employed, then concentration of humus, then ionic strength of the solution, then temperature, pH, method of analysis of the complex, and method of stability constant calculation. So, all these are different factors which can impact the the stability constant of metal humus complexes. And the order of stability constant for metal humus metal fulvic acid complexes was found following this order, where iron followed by L3 plus, then copper 2 plus, then nickel, then cobalt, then lead, then calcium, zinc, manganese, magnesium. So, they are following this stability constant. Okay. In case of fulvic acid. So, obviously, iron fulvic acid complex will be more stable than that of magnesium fulvic acid complex. So, stability constant at higher pH than 3.5 due to higher dissociation of functional groups. Obviously, at pH increases, we know that in case of organic matter, more dissociation occurs. More dissociation occurs means more complex formation. When more complex formation, obviously, there will be greater stability. Also, H plus ion compete for binding site on ligand and hence less metal is bound to lower pH of 3.5. Okay. So, less metal is bound at lower pH of 3.5. So, what is the practical implication of humus metal complexation and metal transport? So, complexation of metal humus prove both beneficial as well as deleterious. So, this there are some beneficial implication. First of all, humic acid reduces a more toxic form of metal. This humic acid reduces a more toxic form of metal, that is chromium 6 to less toxic of chromium 3. Then further, chromium 3 being a Lewis acid forms a stable complex with carboxyl group of humic acid. So, as a result, its availability to the plants and animal is limited. Okay. So, as they are forming the stable complexes with the carboxyl groups of humic acid, they are forming the stable complexes and their availability to the plants and elements is limited. However, what are the negative effects? So, humus serves as a carrier of toxic metals in water by forming stable complexes with them, and these stable complexes of heavy metals are difficult to remove by precipitation because they are making the stable complexes. So, they are not getting precipitated. So, these prove deleterious in water treatment scenarios. So, you cannot strain out, you cannot get it precipitated to separate out. However, the binding of these heavy metals to humus can enhance the biological treatment of the inorganic contaminants. Okay. So, this is how they have both positive and negative effect. Now, in case of plant growth, in case of exchangeable aluminum bound electrostatically on soil colloids such as soil organic matter and clay, and they have very deleterious effects, especially in acidic soil. And in acid soil, when pH is less than 4, enhancing the surface of organic matter content can help in lowering the activity of exchangeable aluminum. How? If you see in this graph, it is quite clear that it is showing the addition of organic matter as the reduction of aluminum concentration, and this increase in organic matter basically we can see in all these conditions lowering the exchangeable aluminum concentration. Okay, lowering the exchangeable aluminum concentration here. However, this effect is higher at low pH condition. So, in this pH condition you can see there is a steep decrease as compared to the higher pH condition like 4.75, and this effect, and this is basically due to the complexation of soil organic matter with exchangeable aluminum, thereby reducing its activity. So, as we are increasing the organic matter, they are getting complex with aluminum and they are basically reducing the concentration of aluminum. In case of lower pH condition, it is better because in case of lower pH condition, the concentration of aluminum is higher than that of higher pH condition. So, effects of humus on mineral dissolution. Obviously, minerals are naturally occurring inorganic solids with a definite chemical composition and ordered internal structures. So, humic substance called dissolution of the minerals, the presence of microbes which produce organic complexing materials can enhance this, and at pH greater than 6.5, humus attack and degrade the mineral form of water soluble and water insoluble mineral complexes. Now also humus can extract mineral from galena, pyrolusite, malachite, different compounds, and they also can extract mineral from silicates, but a lesser degree. Humus also can solubilize various metal sulfides and carbonates ranging from 2100 microgram for lead sulfide and 95 microgram for zinc sulfide. So the next important thing is soil clay complexes. As you can see, this is showing how the soil organic matter helps for increasing the soil aggregation. As you can see, these are the soil microaggregates. These soil microaggregates, how they, different plant and fungal debris can improve these microaggregates, which are varying in different sizes, and also you can see microbial hyphae, mycorrhizal hyphae are there, then particulate organic matters colonized by saprophytic fungi are there, and different clay, these are the clayst microstructures. So as you can see, based on these factors, the soil aggregation is hugely depend on the clay organic matter complexation. Okay. Now one thing is important, that 52 to 98% of the carbon in soil occurs as soil organic matter clay complexes, and soil organic matter forms complexes with clay coated with iron and aluminum oxides, and humus also coats the clay particles, that the surface of such cold clay particles is still reactive. So we can see that organic acids also get absorbed in the interlayer space of expandable clays like Montmorillonite. We have already discussed that in the interlayer space is quite high in case of Montmorillonite. So in this huge interlayer space, soil organic matter can enter and then get absorbed. So mechanism of interaction between soil organic matter K complexes depends on physical adsorption. Three types of adsorption is there. One is and this physical adsorption can be caused by this van der Waals force, and this van der Waals force, it is the when there is a the chance of caused by this physical adsorption caused by this van der Waals force, and the chance that an electron in an atom. So if it is an atom and these electrons in the certain area, the electron cloud, so electrons move, so electron cloud may be at a certain point of time here. So electron charge density at the specific time, the electron charge density must be here, and if all electrons go to the same area at once, a momentary electrical dipole, as you can see, it is a positive pole and there is a negative pole. So as a result of that, a momentary electrical dipole is created. In both this condition, dipole is created, and these electrically negative fluctuation of one atom induces an electrically positive fluctuation, as you can see in the neighboring atom. So this is the neighboring atom, resulting in attractive forces. So due to the orientation of the electrons, the momentary electric dipole which is created can produce the attraction between the adjacent neighboring atoms, which is due to then this is called the van der Waals attraction. Now another bonding is there, that is called electrostatic bonding, and polyvalent cations like aluminum, iron, calcium present in clay surface acts as a bridge between the clay particles and the humus by this electrostatic bonding, and aluminum and iron cations are primary bridge between the clay and humus. We have already discussed that, where calcium is weakly held and easily can be displaced. The third type of bonding is called the hydrogen bonding, results from the linkage between two electronegative atoms through bonding with a single H plus ion. Remember that the hydrogen bonding is weaker than ionic and covalent bond, but stronger than van der Waals forces. Okay. So the last thing which we want to discuss is the retention of pesticides and other organic substances by humic substances. Now pesticides always have a strong affinity for the soil organic matter. So soil organic matter is a very important component in pesticide retention, and soil organic matter affects the bioactivity, persistence, biodegradability, leachability and volatility of the pesticide by their complexes with the pesticide. So the pesticide quantity must be adjusted according to the soil organic matter content of the soil, and pesticides are strongly retained in the internal voids of the humus molecule. They are also adsorbed via ion exchange, protonation, hydrogen bonding, van der Waals force, cation and water bridging and ligand exchange, and humic substances can also combine with non-polar organic compounds via a partitioning mechanism. So, fate of if you see the fate of pesticide bound to soil organic matter, soluble humic complexes can enhance the transport of pesticide in soil and into groundwaters, and fulvic acid, which have low molecular weight and high acidities and are more soluble than humic acid, can transport pesticides and other organic materials quickly effectively. So, you can see how they are affecting the movement of the pesticide by their solubility properties, and how they are importing and how they are affecting the environment by producing these complexes with organic matter and pesticides. So, friends, this makes the this basically ends the whole module of chemistry of soil organic matter. We have discussed a lot from structure of organic matter, and then their carbon cycle, then carbon sequestration, then soil organic matter structure, their humic fractions, their properties, their differences, and also we have seen different types of clay humic complexes, metal humic complexes, and humus pesticide interactions. So, I hope that you have gathered some new information, and these are the references: environmental soil chemistry by Donald Sparks, then Aiken et al. In 1985, they have humic substances in the soil, sediments and water, and Buffle, that is metal ions in biological system, and also Buffle in 1994, that is general chemistry of aquatic systems, which is present in chemicals and biological regulation aquatic systems. So, these are the some of the references you can see. Also, you can consult the Nature and Properties of Soil by Niall C. Brady, so which also discuss in details about the different soil organic matter and their properties. So, thank you very much for listening this lecture, and in the next lecture we will be starting a new module, and let us meet in our next module in week 4. Thank you very much.